last lecture we had spoken about how to compute the Newton steps, that is the delta x, delta y and delta s for solving the system, or rather for solving the Newton system or the system of equations associated with the relaxed KKT conditions. This is what we had already spoken of. Now, what is important for us is that to know that the important step was to know that this is positive definite. So, it has an inverse, because the inverse of this was used. Now, I had told you to figure it out as and complete the rest of the computations, whether how to prove that this is positive definite. So, one thing is that you have to first show it is positive definite. Look, this is I can write XS inverse in this form, because given any positive definite matrix, positive any PhD matrix or positive semi definite matrix, there always exists a matrix A which is also positive semi definite, such that B is equal to square of A, or A is written as the square root of B. So, there is nothing like B to the power half, but just it is a symbolism. So, here I can write this into these two parts, and I have in this way, and I put it here in this place, and then I take the transpose. This is a symmetric matrix. So, transpose is the same thing, then A B transpose is B transpose A transpose, and this is how the things happen. So, now this is nothing but the norm square, and you have this is greater than or equal to 0. What you can show is that this matrix, this is anyway a full rank matrix into A transpose, this has full column rank, has a full row rank, sorry, not column rank, row rank is same as column rank, but full row rank. So, once you can show that these are the full row rank, so this equal to, if this is equal to 0, if and only if this W becomes equal to 0, if this has full row rank, and it is simple to show that it has a full row rank, and that is exactly what you have to show that this matrix is positive semi definite. Now, once we look into the main primal dual framework, let us go to the story once again. You know, we have to solve this equation. We have to solve this equation, that is the relaxed KKT system. So, you know that, so the relaxed KKT system, if you have forgotten, let me write it down once again. So, this is the system that we are intending to solve. Of course, we are intending to have this, but this thing automatically means that I will have this strictly bigger than 0, this. So, as I told you that it is very difficult to really satisfy this equation. So, you want to find some solution which will approximately satisfy this, means maybe that xi si for every I need not be equal to mu, but some number very near mu, that would be enough for our purpose. So, for any x y s which is in f naught, which is nothing but f naught p cross f naught d, for any such thing we will define the duality measure. See, what the final approximate solution that I will get will not give me xi si is equal to mu, but they can, then I will try to see on the average what is the value taken up by the product. So, we will define the duality measure tau as follows. tau is equal to 1 by n summation xi si I is equal to 1 to n or the inner product. So, this is same as the inner product. Now, this tau is central to developing the algorithms, because the solutions of the approximate solutions of these equations will not give me xi si equal to mu. So, they will not be exactly on the central path. So, what I will get is, instead, if this was my central path, what I will get is something here nearby. So, I want to look into take those x and s and try to see. So, I am looking for example, okay, let me look at the whole thing in the XS space, which is much more simpler. X1 S1, X2 S2. Now, any point on the central path would be projected back on this path in the XS space, X into S space. So, unless the point x1 and s1 or x2, s2, x3, s3 whatever, that x and s, they lie on the central path, xs will not be equal to mu. So, the xs point will not be on this straight line. So, it is somewhere maybe here, maybe here, maybe here. So, then what is the corresponding average value that point is satisfying? That is what we call the duality measure. Our aim is to drive the duality measure to 0. So, our aim is to drive tau down to 0, that is do this. Now, all the algorithms, what we will do, we will plan to drive tau to 0, but can we really drive tau to 0? That is the question that we want to answer. So, what we do at every step, we solve this approximate system approximately, get the xis, xisi and try to develop the algorithm in such a way that every step, at each and every step, the mu values, the tau values would continuously decrease. Now, can we really finally reach up to 0? The answer basically is not really true, you might not reach 0. So, what we essentially want is that we fix up a small epsilon naught greater than 0, which is called the precision parameter. And then stop the algorithms, whatever algorithm you have, stop if your tau. So, that xi si, of course, they are strictly bigger than 0, you will stop the algorithm there. Now, what you would get is an xi si, which is whose product xi si where both of them are strictly greater than 0. So, will you really get a point on the boundary? Maybe not, you have not got a point on the boundary. So, what you have done here is that if this is my, so you have stopped someone very near a boundary point, and then there are certain approaches which we will not discuss in detail here. You can move on to the boundary, you can basically, if this is not the BFS, you can move on to the next BFS. You can know that, okay, if I have xis, this is my where I have stopped, let me go on to the next BFS by taking off m minus n points I put 0, then what is the solution, what is the value of xis. So, you can find, so what you do, you find there is a technique of finding the nearest vertex to that point, and that is the required solution. So, but all of these works in polynomial time, means all of these work within a reasonable amount of time. So, what I am going to do here is to solve an equation of this form. So, we are trying to solve an equation, the inexact KKT condition, but we know that it is not possible to find mu e, mu every time for every xi, si cannot be equal to mu every time for every I. So, what we do is, so okay, I do not care, I take the duality measure, I take some tau, which is that there is an initial starting tau, the starting point that you have take its duality measure, and then, so if you have x naught s naught, you take tau equal to basically tau depending on say x naught s naught. So, this will be a starting tau. So, then you use that tau in the equation, and so, but tau you do not, you cannot have tau exactly for every xi si need not be tau. So, what you do, you put in a centering parameter, basically instead of putting mu epsilon in the equations, what you will have is, you will have x s e sigma tau. So, you have not bothered, this sigma tau is acting like your mu, the sigma tau is acting exactly like your mu. So, this is acting like your mu here, the sigma tau where sigma is between 0 and 1 is acting like your mu. So, I cannot find everything exactly equal to mu, but so I am computing the system that okay, everything is not exactly equal to mu, but some fraction of the average, the fraction of the duality measure. So, instead of mu using mu, I am using sigma tau. So, when sigma is equal to 1, then tau is exactly my mu, and when sigma is 0, of course, then I am having the exact solution. So, if sigma is lying in between, then that is not exactly mu. So, it is not giving me a point exactly on the central path, but somewhere as we showed that nearby. So, this is the basic framework. So, sigma, this term, this is acting like a so called, so sigma is called a affine scaling direction, or is acting like a pointer which points towards the central path. So, if I put sigma tau is equal to mu, so my sigma is 1 by times mu, is not exactly mu, but tau is 1 by sigma times. So, mu is some fraction of this tau. So, I am exactly not on the central path, but somewhere else, that is exactly what we are trying to say. So, this sigma tau, if sigma is 1, then tau is mu, then I am on the central path. If sigma is not equal to 1, if sigma is equal to 1, then we are on path, we are on the central path. If sigma is strictly less than 1, then we are not on the central path. So, this is called an affine scaling direction. So, whatever solution we have here of this system, suppose we call this solution, we can write this as x sigma tau. So, whatever solution we have, that is basically the, oh, there is a mistake here, I should have written, oh, just have to rewrite this a bit. I think there is a small, I have forgotten the Newton step. This is equal to, of course, this is 0 0, because we have taken, our points are all coming from, my starting point also be an interior point, x naught, s naught, f naught is belonging to f naught, the interiority condition holds. So, any solution delta x, delta y and delta z, from there you can create a new solution, that is adding delta x to x k, delta y to y k, delta s to s k by putting in certain controls over here. That is, you for example, you take x of x plus alpha delta x is my delta x plus the new one, new thing. So, whatever you get this x plus y plus z plus, which are solutions to the final solutions, and after you get the delta x, this is the new point that I have. These points are pointing in the direction of the Newton solution, pointing in the direction of the central path, right. So, this is called sigma, is also sometimes called sigma, is also called the centering parameter. So, it is trying to force the points to go towards the central path and keep them near the central path. So, let me write down the general framework of an IP algorithm. So, that will give you a fair idea of what we had just discussed. So, the general framework of an IP algorithm, of an interior point algorithm. Okay. So, starting vector. So, you start with some, we assume the starting vector is element of f naught, that is given to me. Accuracy requirement I need, there is a precision, these are given, this is initiation of the algorithm. So, we start with the initialization step, that is, you first initialize x y s with the value x naught, y naught, s naught, starting values, and compute the initial tau, which is 1 by n x s in a product. While, so we will have a while do loop, while tau is bigger than e epsilon, solve, and you know how to solve it. If I put sigma tau equal to mu, we have already showed you in the last class how to solve this system one equation, how to get delta x, delta y, delta s. So, you can just write a computer program simply and which will solve it out. Somehow you can try it at home by writing a computer program, but of course, you have to take matrices of smaller sizes, because you know, unless if you are just working on a PC, there may be a lot of overflows, because when you try to take the inverse, inverting is a very difficult operation, it is a very costly operation in a machine. So, I am telling you from my own experiences of trying, if you are trying to take slightly larger matrices, try to take very small, medium size matrices, say 2 by 3, 3 by 3, and try to check it out. So, this is what you need to solve, where sigma is the centering parameter or the pointer is between 0 and 1. Now, at every step the new x y s would be nothing but x y s into this, into x y s is assigned the old x y s plus alpha times delta x, delta y, delta s. So, the alpha is called the scaling direction, scale parameter, or the scaling scale. So, this scale parameter alpha has to be chosen between 0, of course, it cannot be 0, that is not fair. 0 means you are talking about the exact solution, but that is not possible. So, alpha is between 0 and 1, which is a interval excluding 0, and this denotes my suitable scale parameter or step size. So, it is also called step size. So, it is a while do loop, while do this solve this, and once you get the new value x y s, again assign to tau, I think you should have put in that, assign to tau the new one. So, end while end. So, what you do is again you check if tau is, so my new x y s is this, my new tau is this, check whether tau is this, and again go back and solve this and continue. So, when tau is less than equal to epsilon, you stop the whole thing. So, what would be a suitable step size? So, that depends, sometimes alpha in the short step path following method, which we will start studying tomorrow, you will have alpha is equal to 1, and that will be giving you a lot of. So, sometimes for when I am not writing an algorithm you can write these assignment parameters, and so it looks like a program, but in general I would, what people would do, people would write x alpha or x plus, does not matter, y alpha, it depends on the alpha, s alpha is nothing but equal to x y s plus alpha times delta y delta. Now, in order to study the algorithms, it is very important that we make certain estimates. These estimates will tell us whether what we are doing is true, is correct. So, if I design an algorithm, I have to show that if I run my algorithm, I will finally go and get what I desire, I will get tau strictly less than epsilon in certain steps. That has to be, that is what is called the convergence analysis. So, every algorithm we need to do a convergence analysis, in the sense that whatever algorithm I am writing, it is making sense, that it is working has to be proved mathematically. So, let us look at an estimate that will require quite often is this. Okay. What is this? Now, how do I go about solving this? Look, if I look at the equation, then what do I have? If I look at the equation, this one. So, I would have A transpose delta x plus delta y equal to 0, and I will have A transpose delta I will have A transpose delta y plus delta s equal to 0, I will have A delta x equal to 0. So, from the Newton's equation, from the Newton system, so I will have A transpose delta y plus delta s is equal to 0. Also, I am having A of delta x is equal to 0. Now, from the Newton scheme, from the, so I will now write this as this Newton scheme as a star scheme, as a main scheme from the Newton scheme star. So, what would I have? Now, this means delta s I can write from here, which is nothing but minus A transpose y. So, this A transpose delta y. So, instead of delta s I have written this, taking the minus sign out. So, now I can write this as A of delta x, but what is A of delta x? It is 0. So, I get 0. So, we have this conclusion that if you take the Newton steps of x and s, first and third variable, you get 0. Now, an interesting question is, can I compute the value of tau alpha? Tau alpha of course means so can I relate, see tau alpha has to be such that it has to be smaller than tau, because my tau has to go down. That is exactly what I want, because I want to drive my tau towards 0, and that is the whole ball game. Can I relate tau alpha with tau so that we can be sure that the value of the duality measure is coming down? So, let us see how can we do this. Look at the last row of the equation, this row, s of del x plus capital X of del s is this. So, I want to compute tau alpha. So, let me look at the last equation. So, it will give me s of delta x plus x of, this is from the star equation, from star. Okay. Now, I look at it component wise. So, this is a vector x1, s1, x2, x2, this is a vector sigma mu, sigma mu, sigma mu. Now, I also want to look at this component wise. This will become this s1, s2 dot dot dot, then it is s1 delta x, s2 this delta x1, delta x2, delta x3. So, let me look at it component wise, what will happen, right. So, S is a diagonal matrix consisting of S1, S2, Sn in the components. So, if I look at that, let us see what actually happens. If I write this in a very broader way, I would have so here if I write it down more clearly, so the first equation here would be S1 delta x1 plus x1 delta s1 to minus x1 s1 plus sigma mu. So, here there is a mistake, this is sigma tau epsilon. So, it should be sigma tau. If you look at the equation, it is sigma tau, not sigma mu, sigma tau here. So, sigma tau and sigma tau. And so on. So, I can write Sn xn delta Sn sigma tau sigma tau. Now, I will write the definition of sigma tau and then you will immediately see this will give me sum up all these equations. So, if I sum up all these equations, we have the following, that is S of delta x, x is a vector S1 S2 Sn, plus x of delta S is minus x s plus, now you add, there will be sigma n tau is again sigma x s by n. So, you will get sigma x s, that is what it is. Now, I will do n into tau alpha is equal to x alpha S alpha, that is the definition. Now, I will write down what is x alpha. X alpha actually for me means x plus alpha into delta x s plus alpha into delta s. So, I will now do their detailed computation. Let us compute out, tau n tau alpha. So, what I have is n tau alpha is equal to, I am just repeating what I wrote in the last thing, s plus you will see the estimate delta x into delta s will be useful here. So, now what I will have is x plus alpha delta x into s plus x plus alpha delta x into alpha delta s. So, I have x of s plus alpha times delta x into s by just using the properties of inner products, plus x alpha into x delta s plus alpha squared times delta x delta s. Actually, it was important to estimate this because we needed to find out tau alpha, that was the reason to actually estimate this. In real research, this thing came much later. First one tried to compute this and then this thing was computed. So, that we know that we actually have to drive this part to 0. So, anyway, we now know that this is 0. So, we have x s plus alpha times s delta x plus x delta s, and this is something we have just computed. We have just computed this to be x s plus alpha times, this is nothing but minus x s plus sigma x s. So, it is becoming x s minus alpha x s plus alpha sigma x s. So, what I can write here is x s, I can take out the x s as a common thing. So, I will have 1 minus alpha into 1 minus sigma x s. But what is x s? It is n into tau. So, it is n into 1 minus alpha times 1 minus sigma times tau. So, n into tau alpha is this. So, what I would now have is tau alpha is 1 minus, again go back, alpha into 1 minus sigma, alpha into 1 minus sigma times tau. Now, alpha is a quantity between 0 and 1, sigma is also a quantity between 0 and 1. So, this is less than 1, this is less than 1, this product is less than 1. So, 1 minus this something is bigger than 0. So, into tau. So, tau alpha is a fraction of tau. So, what we have concluded that tau alpha is a fraction of tau, and that is what we require, the value should come down. Okay. Now, how does the algorithm behave? If we are claiming, we claim that our algorithms of the interior point type or the IP type are of polynomial time. What do we mean by this? This is something we really have to concentrate on now. So, what we have shown that in our general framework of IP algorithms, we can reduce the tau alpha, the duality measure, which is of fundamental importance. So, we have already built up something. Now, what we want to show is that we can develop some framework. In this current framework, we can put in some sort of little conditions which will immediately lead us to a polynomial time game, because in the sense that it will show us that okay, I can give you the number of steps in which your algorithm will terminate, and that number of steps is not arbitrary, that number of steps is bounded on the above by a polynomial. So, if you know your number of variables in the decision variables, you can tell me in what number of steps you will lead to the solution. Now, this is what we are going to discuss tomorrow. How can we show that our general framework of the IP algorithm, which we have done, which is actually this one is called the general IP algorithm. So, algorithm is polynomial time. Basically, the idea is this: you have a fixed x naught, y naught, s naught, and that you have fixed in f naught, and now you start the algorithm. You start with tau naught and you are now pushing the tau naught towards 0. Now, this is your epsilon is your precision parameter. Now, find the number of steps say k, so that in k steps we have tau is less than, this is just tau. So, I start with this and I have to show under what situations I can have I can compute the number of step size k, and we can show that number of steps that k that is required till we come to this is actually bounded by a polynomial, which tells us that okay, this is the maximum number of steps you would require to reach this. You won't need anything much more. Such a thing cannot be guaranteed for the simplex algorithm, though it is amazingly effective in practice. So, tomorrow our first job would be to start with proof of the polynomial, proof of polynomial time. Proof of polynomial time, and then once we have the proof of polynomial time, we will start with something called short step path following algorithm. We will do its convergence. So, the number of methods that we learn here are following: the short step path following, the long step path following, of course, and there is something called the predictor corrector method. And then once we know about the predictor corrector method, we will also give a brief outline of Sanjay Mehrotra's predictor corrector method, which is the most useful predictor corrector method that is used in algorithms. We will try to, if time permits, to briefly touch on what is called the potential reduction algorithms, which is also a type of IP algorithms. So, with this we end the talk here, and tomorrow we will start with proving the polynomial time and then get into these algorithms. So, that we would need around 3-4 more lectures to have a brief idea about these things, and we will give references from which you can do your further studies.